So today what we'd like to do is return to the discrete time Fourier transform and finally dig into it a little bit and see if we can understand how it is that we compute the discrete time Fourier transform and begin to see some of the information that we can glean from the discrete time Fourier transform. What are some of the characteristics of signals and systems that we can learn from this new transform? The notes that you need for this lecture are posted on PolyLearn, so please download those and follow along and fill in your additional notes where you need to. So last time we looked at the discrete time Fourier transform and came up with the definitions for it and spoke about when that transform will and won't exist. So today we're ready to start talking about how we can actually use the discrete time Fourier transform formula to compute the frequency spectrum of signals or the frequency response of systems. So we'll take a simple example first and find the discrete time Fourier transform of a simple time signal, the most simple, a unit sample sequence, delta of n, where delta of n, of course, is defined as having a single unit sample with a value of 1 at n equals 0 and is 0 otherwise. If we take the definition of the discrete time Fourier transform, we know that the transform is the sum from n equals minus infinity to plus infinity of the signal that we're trying to transform, x of n, and the complex exponential e to the minus j 2 pi n capital F, where capital F is our variable for the discrete time Fourier transform. It's the thing we've been calling digital frequency, normalized frequency, which is the analog frequency divided by the sampling rate. The very same frequency we've been using all along since we've been talking about sampling theory. So in the defining equation, we replace x of n with the actual function delta of n. And knowing the characteristics of delta n, we can simplify this summation. We know delta of n is 0 everywhere except n equals 0, so the summation actually degenerates to a single value at n equals 0. And at n equals 0, delta of n equals 1. So we only, out of that whole summation, we get only a single exponential term, which is 1 times e to the minus j 2 pi n equals 0, and f. In our exponent, we have a 0 multiplier, so the whole exponent goes to 0. And we have the simple result that the discrete time Fourier transform of a unit sample sequence is a constant value, a 1. Now that's not a single one sample value, that's a constant value of 1 at all frequencies. So there we have our first derived discrete time Fourier transform. And if you recall continuous time Fourier transforms, the impulse function, delta of t, also had a continuous time Fourier transform of 1. Now taking a simple signal made up of 3 values, only 2 of which are non-zero, but this happens to be one that's not causal. At n equals 0, this signal is 0. At n equals minus 1, it has a sample value of 1/2. And at n equals plus 1, it has a sample value of 1/2. So if we applied that signal, we can, even though it's not causal, we can certainly still compute a discrete time Fourier transform for it. And we'll use the defining equation again and replace the x of n in the summation with the actual values that we have. And again, we only have 2 terms in the whole summation where x of n is not 0. So the whole summation in this case breaks down to only 2 sample values. At n equals minus 1, x of n equals 1/2. So we get the first term 1/2 e to the minus j 2 pi times minus 1 times f. And for the n equals plus 1 term, where x of n equals 1/2, we get the second term in the summation plus 1/2 e to the minus j 2 pi times 1 times f. Cleaning up those exponents, we have that the discrete time Fourier transform is a 1/2 e to the plus j 2 pi f plus 1/2 e to the minus j 2 pi f. And you may recognize that as an Euler identity for a cosine function, where the angle argument of the complex exponential becomes the angle argument of our cosine. And so the discrete time Fourier transform of this interesting sequence of 1/2 at -1, 1/2 at n equals +1 gave us a cosine function. So that's a cosine 2 pi f. Now that looks like a cosine that we're familiar with, but this is a cosine in terms of the frequency variable f. F is our independent variable. We don't have a time variable in here anymore. So f is not continuous, f is not a constant, it's a changing value in this case. Now, we would normally want to look at the magnitude and phase of the discrete time Fourier transform because in general it's a complex function. Now in this case it's not. We have a real valued function. We can still talk about plotting the magnitude and phase of this function, or we could talk about plotting just the whole functional value, cosine versus frequency. If we cast it into our normal way of describing transforms, breaking them up into magnitude and phase pieces, we would plot the magnitude of the cosine function, which does go negative at times, and so that would be a different function than just the pure cosine 2 pi f. The phase angle then, it's a real function, but the phase is not technically 0 everywhere. Anywhere that cosine function gives us back a negative value, I would have to account for that by applying 180 degrees of phase. In terms of instead of radian phase, it would be a plus or minus pi radians of phase. So if we were plotting this as magnitude and phase, we would plot the magnitude of the function, magnitude cosine 2 pi f, for the magnitude spectrum. And for the phase spectrum, anywhere that the cosine function is positive, we would show a 0 phase. Anywhere the cosine was negative, we would show either a positive pi phase or a negative pi phase. Now, we haven't proven this yet, but because of the looking ahead to the symmetry that we expect for real valued functions in their Fourier transforms, we actually know that the magnitude response should be an even symmetric function around f equals 0, which that cosine function is. The phase function should be an odd symmetric function around f equals 0. And so if we chose, for example, to use minus pi phase for positive frequencies where the cosine function goes negative, technically we would have to use a plus pi phase for negative frequencies where the cosine goes below 0. But that's a detail we can get into as we go further along. Now the discrete time Fourier transform is in general an infinite summation formula, and depending on whether we're working with finite or infinite length sequences, we may or may not have to sum an infinite series or a finite series. And there are some summation formulas for infinite series, particularly for exponential series, that will come in handy when we're using this transform. Hopefully you've seen these before in your calculus classes, but just as a reminder, if we have a summation from 0 to infinity of some constant raised to the n power, so this is an exponential geometric series, that sum, as long as a, the magnitude of a is less than 1, or in other words, as long as a is a fractional value, that sum does converge, and it converges to 1 over 1 minus a. As you can readily see, if the magnitude of a was greater than 1, then we'd be summing bigger and bigger and bigger values. That summation would not converge. For a finite series of length n that goes from little n equals 0 to capital N minus 1, if we were adding up exponential terms for this kind of finite length sequence, so we have a 1 plus a squared and so on, that finite series adds up to the value 1 minus a to the capital N over 1 minus a. So these are two summation formulas that when we're evaluating the discrete time Fourier transform, or for that matter in the future with Z transforms that are also a infinite summation formula, we may need these for doing those computations. So now let's take an exponential sequence. X of n is alpha to the n u of n. Alpha could be any value as long as it's a fractional value. It could be positive or negative, but it must have a magnitude less than 1. because we're going to want to put that in our infinite sequence or infinite series and have that converge. So we'll need the magnitude of alpha to be less than 1 for that to happen. So plugging that x sub n equals alpha to the n into our discrete time Fourier transform formula, well, x sub n gets replaced with alpha to the n. Now what we do with the u of n is change the limits of the summation, because x sub n is 0 for all values of n less than 0. We don't need to sum up the negative n terms. So we can raise the starting index for our summation to n equals 0. And that's how we account for the u of n. And I can then drop the u of n from the explicit expression. So we have a sum from n equals 0 to plus infinity of alpha to the n, e to the minus j 2 pi nf. And we can simplify that by pulling out an exponent of n that goes with both of the alpha and the exponential terms. And now we have a sequence that looks like one of our infinite sums, an a to the n kind of sum from n equals 0 to infinity, that has a sum of 1 over 1 minus a. So we take 1 over 1 minus everything in the parentheses of the summation, and that was alpha e to the minus j 2 pi f. That would be the discrete time Fourier transform of this exponential. And for a particular alpha, we would just plug in the value of alpha into this expression. Now, this is a complex result because we have that complex exponential in the denominator. If we wanted to break this up into magnitude and phase, well, we would have to break up that exponential perhaps using an Euler identity, where the e to the minus j 2 pi f becomes cosine 2 pi f minus j sine 2 pi f. And distributing through the minus alpha in front of that gives us this denominator shown in blue of 1 over 1 minus alpha cosine 2 pi f plus j alpha sine 2 pi f. For the magnitude of that, we would take the magnitude of the numerator divided by the magnitude of the denominator. And for the magnitude of the denominator, we would break up this into the square root of the sum of the squares of the real part and the imaginary part. In this case, the real terms are 1 minus alpha cosine 2 pi f, and the imaginary part is alpha sine 2 pi f. Putting those together under a square root and expanding out the quadratic that we have there, that would expand to 1 minus 2 alpha cosine 2 pi f plus alpha squared cosine squared 2 pi f. And the second term that came from the imaginary part of the denominator gives us another alpha squared sine squared 2 pi f. And as you can see, we have a cosine squared plus a sine squared with the same leading coefficient, so we can combine those together, and we'll have alpha squared times quantity cosine squared plus sine squared, which is just 1. So that leaves us a denominator of the square root of 1 minus 2 alpha cosine 2 pi f plus alpha squared, and that would be an expression for the magnitude of the discrete time Fourier transform. And if I wanted to see a magnitude response, I would plot this function, which is a real valued function, against capital F frequency. In terms of phase, we would take an inverse tangent of the denominator, the numerator minus the denominator. And so the angle of the numerator is just a value of 1, so that would be 0. The angle of the denominator would be the inverse tangent of the imaginary part over the real part. So we have an inverse tangent of alpha sine 2 pi f over 1 minus alpha cosine 2 pi f. And the correction that you should make to that slide is that's the term in the denominator, so we need a negative sign out in front of that inverse tangent. Plotting that function then, and here it is shown properly, we would plot the magnitude response as shown in this top plot, and the phase response would have the shape shown in the bottom response, again plotted versus digital frequency. just plotted as a function of a continuous function of f. Again, f is a continuous function. It's not a sampled value function. The particular graph shown here is for the particular value of alpha equals 1/2. So notice, as we expect with a discrete time Fourier transform, this is a function that's periodic. It repeats with every integer value of the digital frequency, which relates to the integer multiples of the sampling rate in analog frequency. So notice in the magnitude response, we get a peak at digital frequency 0. That peak is repeated again at digital frequency 1 and -1, and actually repeats so on at frequencies 2, 3, 4, and in the negative direction as well. Likewise, notice we have a periodic function in the phase response as well, repeating with the same period of repeat. The dark vertical lines in the plots show the extent of the principal range between -1/2 and +1/2. And so as you see, we capture a complete representation of the function when we look at it in the principal range. Now, the discrete time Fourier transform is generally used for two purposes. For either, if we apply it to a signal, the result that we'll get is telling us something about the frequency content of the discrete time signal. What frequencies are present in the signal and how much of them are there. If we apply it to the unit sample response of a system, then the discrete time Fourier transform gives us the frequency response of that discrete time system. And we can arrive at that either by directly taking the transform of the unit sample response, or we can actually derive the frequency response directly from the difference equation by transforming the equation term by term and rearranging it. And we'll look at that next time. And what that looks like if we had a discrete time signal and took its discrete time Fourier transform and plotted it versus frequency. So for example, if we took the sound of a trumpet playing, it would have a frequency spectrum that might look something like this. And if we went between the Nyquist rate and in both the positive and negative frequency representations, we would see this symmetrical spectrum, magnitude spectrum that has peaks at the harmonics of the note that's being played by the trumpet. Now, because the discrete time Fourier transform is a periodic function, we would expect to see this particular spectrum repeating over and over and over again, infinitely in both directions. So technically, again, the discrete time Fourier transform is a periodic repeating function. If we apply the discrete time Fourier transform to a unit sample response and get a frequency response of a system, then we get a plot similar to the one we saw in the previous slide. Again, it should have the same repeating patterns and symmetries that we expect, centered or with some centered around f equals 0, excuse me, and looking in the principal range from -1/2 to +1/2, we see one complete cycle of the discrete time Fourier transform, both the magnitude and phase, and that cycle repeats every integer value of the digital frequency. So for computing a frequency response, we would begin with the unit sample response of a system, which is a discrete time function, or h of n, take its discrete time Fourier transform, and whatever results of that transform is by definition the frequency response of the system. And we would apply the definition summation to make that computation. Sum from n equals -infinity plus infinity, h of n, e to the minus j, 2 pi, and f. Again, that's a periodically repeating spectrum with a period of 1. Now sometimes we need to go the other way. We need to go from want to go from a frequency response and recover from that the unit sample response of the system, or we want to go from a frequency spectrum of a signal and recover the signal itself. For that, we would need an inverse discrete Fourier transform, and that's given by this equation here. If you have the frequency response of a system, hp of f, where the little p is a subscript that we use to remind ourselves it's a periodic function, and it's a function of the continuous variable f. Because it's a continuous function, we can't use a summation to recover h of n. We actually have to use an integral, an integration over the continuous function capital F. And in this case, we would integrate only one copy of the repeating spectrum. So we generally would integrate over the full principal range from f equals -1/2 to +1/2. The discrete time Fourier transform value, hp of f, that function, now multiplied by, again, a complex exponential, this time with a positive sign, the exponent, e to the plus j 2 pi n f, and df for our differential frequency. So again, that's an integral over one period of the repeating spectrum within the principal range. The result of that integration will give us back the time domain function. Now, how do we compute the discrete time Fourier transform? Well, we've already done a few examples. We'll do a few more and try to illustrate that there's more than just one way to do this. We have several options for doing that computation. We can go ahead and use the defining summation, the transform definition, as we've done already. Once we've developed a number of these, we can stop doing the applying the definition and actually get our discrete Fourier transforms for some common signals from lookup tables in a textbook or in these presentations, and using those lookup values and perhaps modifying them a little bit based on some properties of the discrete time Fourier transform, we can usually do the transformation without having to resort to the actual summation. And finally, when we get particularly to looking at frequency responses, we'll have another way that we'll be able to quickly derive the frequency response of a system by applying, again, the tables and a particular property of the discrete time Fourier transform, the time shift property, that will allow us to develop the transfer function or the frequency response of the system directly from the difference equation. So we'll have several options. Let's take a look at how each of these will work, and again, learn a little bit about what we can glean from this information that we get out of the discrete time Fourier transform. So going back to examples of using the defining definition, the h of f is the sum of h of n e to the minus j 2 pi n capital F. Now, if we have a finite length sequence, or the unit sample response for an FIR filter, for example, then we can do as we've done in the first few examples and simply write out the individual terms, the individual non-zero terms of this summation, and then work with the complex exponentials to simplify them as much as possible. So if we explicitly write out the terms of the summation, we would have some, for each value of n, we'd have some h term, and we'd have an e to the minus j 2 pi nf term, and we would just sum along all the ones for any value of n where h of n is non-zero. As an example of that, here's a non-recursive finite impulse response filter. We have x of n coming in on the left, y of n coming out on the right, and with the delay block and the block diagram given, we could hopefully recover the difference equation that describes this filter very quickly. The output y of n is just 1/2 times the signal coming in x of n, plus another 1/2 times a one sample delayed version of x of n we call x of n minus 1. Now that's the difference equation for this filter. If we want to find the frequency response for this filter, we're going to need the impulse response, because that's what we'll transform to get the frequency response. And as we've mentioned in class, for FIR filters, they're particularly easy to find the impulse response for, because we just substitute x sub n with a delta sub n, and whatever comes out then is the unit sample response. So if we replace x sub n with delta sub n, our difference equation becomes 1/2 delta of n plus 1/2 delta of n minus 1. Or the equivalent way of looking at that is that we know that the sample values for the unit sample response will exactly match the filter coefficients, the B coefficients in our difference equation. And so for sample values, we have the 1/2 for the B0 term plus another 1/2 for the B1 term. Both these expressions would be equivalent ways of describing the unit sample response. From this, now we would like to find the discrete Fourier transform of that impulse response so that we can find the frequency response of this particular filter. So if we're working with the defining equation, we would write out the sum terms of the discrete time Fourier transform definition for all the values of h of n that are non-zero. In this case, we only have two. We have n equals 0 term and n equals 1 term. So writing those out, we have the h0 term with e to the minus j 2 pi n equals 0 times f added to h1 e to the minus j 2 pi 1 times f. Substituting in the 1/2 for h0 and h1, we'd have this expression for the discrete time Fourier transform, and where we recognize in the first exponential 1/2 e to the minus j 2 pi 0 f, that's the same as e to the j0, and e to the j0 just has a value of 1. So simplifying this, we have the discrete time Fourier transform, where the frequency response of this system is a complex function that's made up of 1/2 plus 1/2 e to the minus j 2 pi f. Now, if we'd like to plot that function or break it up into its magnitude and phase components, we'll need the help of some Euler identities. We have an exponential here, but we only have one term with an exponential. If we're going to make it look like one of the two Euler identities, either a sine or cosine function, well, we'll need to have two exponentials, one each with the same exponent, only differing in the sign, and they must both have the same coefficients out in front. Now we do have the same coefficients. We have 1/2 in both terms, but I have one of these expressions with an exponential, one without. So actually, to simplify, we're going to back up a little bit and undo some of the simplifications that we've done to make it easier to break this up into magnitude and phase. If I take that 1/2 and express that as 1/2 times e to the j0, because e to the j0 is the same as 1, then I've got something that's beginning to look like, well, in this case, a cosine, because I have a plus sign between the two terms. And I also have the 1/2 that I need, which is helpful. However, I don't have the same exponent. I don't have e to the plus j something and e to the minus j something in those two terms. In order to arrive at that, what we can do is factor out a factor of e to the j, and what we want to take out is a value that's halfway between the beginning and ending exponent. So halfway between positive j0 and minus j2 pi f. In this case, that would be an e to the minus j1 times pi f. And when I pull that out, the first term becomes a 1/2 e to the plus j pi f, and the second term becomes 1/2 e to the minus j pi f. And when I put those back together, when I combine the e to the minus j pi f with the 1/2 e to the plus j pi f, I get back to 1/2 e to the j0. Likewise, when I recombine e to the minus j pi f with 1/2 e to the minus j pi f, I get the 1/2 e to the minus j2 pi f. Now the function in brackets looks like exactly like a cosine, where the theta is now pi f. So I can replace this whole function with a cosine of the argument pi f. So a simplified version of this discrete time Fourier transform, this frequency response function, would be e to the minus j pi f times cosine pi f. Now, you may be saying, well, that's not very helpful. It's still a complex function, but we've actually broken it up in a way that makes it easy to isolate the magnitude components and the phase components. If we take the magnitude of this complex function, well, it's a product of two functions. It's a complex exponential multiplied by a cosine function. So if we want the overall magnitude of the product, we would take the product of the first function times the product of the second function. And the magnitude of that exponential function would be the magnitude of cosine pi f, should be minus j sine pi f, and the second term is a cosine pi f. But the magnitude of the first function there, the complex exponential, degenerates into a cosine squared plus sine squared, which we know is just 1. And so the magnitude of this function is just the magnitude of cosine pi f. So here we see the value of breaking out that complex exponential term by itself that has a magnitude of 1 and doesn't affect the magnitude response at all. And then we're left with a real function, cosine pi f, whose magnitude is simply the magnitude of that function. The phase response then, well, it's again a complex product, even though the second term is a real term. So to find the overall phase of that product, we would take the phase of the first function, add it to the phase of the second function. And the phase of the complex exponential is just the angle argument of the complex exponential, in this case minus pi f. And again, the cosine function is a real function, so typically we ascribe it as having a phase of 0. However, again, as in the previous example, anytime that phase goes negative, we need to account for that in anytime the magnitude of cosine goes negative, we have to account for that with a either plus or minus pi phase. So we'll add this extra term to show that sometimes we're adding 0 when the cosine is greater than 0, and anytime the cosine function goes negative, we have to add either a positive or negative pi to the phase of the overall function. So again, that would look like this if we plotted a magnitude of a cosine pi f versus f. Well, it's one that's going to go to 0 at f equals 1/2 and minus 1/2. At f equals 0, the cosine gives us a value of 1. And where the cosine function would normally go negative, since we're plotting the magnitude, that negative lobe gets flipped up to be positive, and we end up with a function that has the sort of symmetry around f equals 0 that we would expect for a real valued time function. The phase response is a straight line. It's minus pi times f, so that's a linear function of frequency. And that wraparound, you'll notice it's jumping by a pi phase every time that the magnitude response goes to 0. Those jumps are those additions of either pi or 0 or minus pi that are happening when the magnitude flips sign. And so we wouldn't consider those a true discontinuity in the phase. And this phase actually has a very interesting characteristic. Now, if we look at the magnitude response, we can ask ourselves, if I wanted to classify this filter as either high pass, low pass, band pass, or band stop, what would we call this filter? And so looking at it, you might be tempted to say, well, it looks kind of like a band stop or a notch filter, where you have these periodic places where the function goes to 0, where we would be eliminating those frequencies, and other places where we have peaks that are at a magnitude of 1, which means we're not going to attenuate those frequencies. However, even though that's what our eyes tell us, in in reality, this would be considered a low-pass filter. Notice that what would be low frequencies would be ones near frequency 0, and there we have a magnitude of 1, so we're not attenuating any signals there. And what's the highest possible frequency that we can put into our discrete time system without it aliasing? Well, it's the Nyquist rate, which would be at f equals a half. So here, in this upper part of the principal range, is what we would consider the high frequency range, at least the highest allowable frequencies that we can put in, and around 0 would be what we would consider low frequencies. So this is a filter that passes low frequencies and attenuates high frequencies. So that would be a classic example of a low-pass filter. Now, it's not a very good one. It's nice in the sense that it doesn't attenuate DC, as we would expect, but it really doesn't attenuate high frequencies very well at all. It lets quite a lot through, all the way up to the Nyquist rate. But technically, this would be considered a low-pass filter. Now, as we began to mention this a moment ago, this phase characteristic where we have a straight line in the phase, even though these little discontinuities, that's actually a very unique and very helpful kind of phase response. That's what we would call a linear phase response, because it's a linear straight line function of frequency, where in this case the slope is a -1. And that's the characteristic of a filter that's not introducing any phase distortion into our signals. What this straight line phase plot is telling us is that this low pass filter, as crummy as it is as a low pass filter, one of the nice things that it does is that it doesn't realign signals of different frequencies. It doesn't distort their phase when I put a signal through this filter. In fact, what this filter does is introduce a pure time delay into a signal, which means it's going to shift in time all frequencies uniformly so that they all shift the same amount of time, even though that requires a different amount of phase depending on what frequency you're putting in. And in fact, there's a linear relationship between how much phase you have to introduce to time shift all the different frequencies uniformly. So our recursive filter has that interesting characteristic. To illustrate this again using a non-recursive filter, we could use this, I'm sorry, it's my apologies. Going back to this example, we have our non-recursive filter, an FIR filter, that had a difference equation y of n equals 1/2 x of n plus 1/2 x of n minus 1, with a unit sample response that had two values, 1/2 and 1/2 at n equals 0 and n equals 1. From that, we derived its frequency response that had a magnitude response of magnitude of cosine pi f, and it had this interesting phase response that we said was a linear phase response. It was a straight line relationship between frequency and phase, and that we said was indicative of a pure time shift. Now we can dig into that a little bit to understand that a little bit better. Let's look at how phase and time are related in our cosine and sine functions. Here's a generic discrete time cosine signal. It's cosine 2 pi f0n, where capital F0 is any valid digital frequency. And if we looked at what happens if we take that function and delay it by n samples, so we'll introduce an n delay, a number of samples. So instead of x of n, we're now making x of n minus n delay. In terms of our cosine function, we'll just change the index from n to n minus n delay, and look at what that means in terms of phase of our cosine function. To do that, we'll distribute the 2 pi f through the phase terms, and we have our cosine 2 pi f0 n minus 2 pi f0 n delay, where that minus 2 pi f0 n delay represents the amount of phase that's introduced into the cosine function by a time shift of n sample values or n sample intervals. So that's an additional phase function we'll call theta of f. And if we double check the units on that phase function, we should get something that looks like an angle argument, radians. The 2 pi is radians per cycle. The f0 is digital frequency cycles per sample. And our n delay is in terms of number of samples. And if we cross out the different like terms, we find that we do in fact end up with a radians argument. So we are dealing with real phase here. And that phase term as a function of frequency is minus 2 pi n delay times f frequency. And 2 and pi and n delay are just constant values. So we have a phase function that relates to frequency through some constant k. And we have a linear relationship between phase and frequency that's introduced whenever we introduce a delay in a signal. So for a time delay, to shift all frequencies by the same amount of time, we have to introduce a different phase, a phase that depends on what frequency your signal was, and there's a linear dependency, a linear relationship between the amount of phase that you need to introduce and the frequency that you're trying to shift the same amount of time. The higher the frequency, the more phase you have to introduce in order to get the same time shift in that function. And again, if we were plotting a phase, linear phase response like this, we would get something that would have to wrap around whenever we hit 2 plus or minus 2 pi. But in between those places, it would be a straight line function, where that slope in this case would be exactly minus 2 pi times however many samples we were delaying our signal. To illustrate this, let's take a sinusoidal signal, in this case a 1 Hertz sine signal, and we'll look at it in continuous function just to make it easier to see instead of a discrete time function. Now if I move that over and delay that sinusoid, that cosine signal, by a quarter second, and that's the dotted line shown here. Now if we ask ourselves, what fraction of a period did we traverse in that waveform when we shifted it by a quarter second? So in that at 1 Hertz, when we shift by 0.25 seconds, in terms of how much of a cycle, we've gone ahead by a quarter cycle, or pi over 2 radians in terms of phase. So you'll notice where the original function is at the peak of the new dotted function, it's moved ahead, it's advanced by a quarter cycle or pi over 2 radians. Now if we do that exact same thing with a function that has twice the frequency, a 2 Hertz signal, but still shifted by the exact same amount of time, a quarter second, and look at how much of a cycle did we traverse now in the 2 Hertz signal for the same time shift. Well, here we've advanced half a cycle, or pi radians, in the 2 Hertz signal, and it was only a quarter cycle, or pi over 2 radians, in the original 1 Hertz signal. So when we doubled the frequency, the same time shift represented twice as much phase, twice as much of a phase change. So there we see that linear relationship between frequency and phase when we're talking about a pure time shift. Now we use 2 different metrics for the amount of phase delay and the phase linearity in a frequency response of a filter. And these were the same metrics that came to us from continuous time systems. First is the phase delay that's introduced by a filter or a discrete time system, and the group delay. Now, these are two different measurements of two different equivalent time shifts that are introduced by phase functions in a filter, or phase responses. The one way to think about the difference between these is that the phase delay is basically if I took the actual value of the phase response at one particular frequency and converted that directly into how much of a time shift or time delay does that represent. That would be the phase delay in time units. The group delay looks at what's going on in a range of frequencies around some particular frequency. And so it infers a phase amount or a time shift amount from the slope of the phase curve as opposed to the numeric values of the phase. Now that may be hard to interpret from words, so let's look at a picture. And we can see the difference in the functional descriptions. Both these have 1 over 2 pi's out in front, but the phase delay takes an actual value angle from the angle argument of the frequency response at a particular frequency. The group delay uses the slope of the angle function versus frequency. Now, in discrete time, we use a similar kind of definition, except for now we're working with the discrete time Fourier transform, and we're looking at the slope of the DTFT phase response curve. So here, for example, is the filter we've looked at already, recursive IIR filter. And if we wanted to know what was the group delay and the phase delay of this particular filter at the particular frequency shown F0, the difference would be that if we wanted to know the phase delay, we would find F0, we would go to the phase plot, find what the phase value is, extrapolate that back over, take that phase value and plug it into the formula here, minus that phase amount divided by 2 pi F0 would be the phase delay. If I wanted to know the group delay, then I would again go to that same frequency, but instead of picking off the particular phase value, I'd look at the slope of the phase curve at that particular frequency, d theta df, take that slope value and plug it into the group delay formula, divided by 2 pi f, put a negative sign out in front, and that would be the group delay. So we can think of the group delay as representing the equivalent time shift that particular frequency is experiencing, whereas the phase delay is really a pure phase measurement. So now, what kind of filters are these that have this interesting characteristic of having a linear phase response or linear relationship between phase angle and frequency? Well, some, but not all, FIR filters have this. In fact, no IIR filters can have completely linear phase. IIR filters may have some portions of their phase response that looks pretty linear, but they can't have a completely linear phase over all frequencies, whereas there are some classes of FIR filters that can, and in fact this makes them very attractive for certain applications. And this is one place where discrete time filters are different from continuous time filters. With discrete time filters, I can make FIR filters and I can make linear phase FIR filters. That's not something I can do with analog filters with op amps and capacitors and resistors. I don't have the ability to make completely linear phase filters. The other characteristic that brings on this linear phase response is a symmetry that shows up in the unit sample response. In fact, for a filter to have this linear phase response, the unit sample response h of n has to have some symmetry around its center point. It can be even symmetric around its center or odd symmetric, it doesn't matter, but as long as it has one of those two symmetries and it's an FIR filter, I'll have a linear phase response in my discrete time Fourier transform frequency response. Now, why do we like this? Well, a filter that has linear phase response we say it has no phase distortion. If it has a linear phase response, then that is telling us that it's time shifting all frequencies by an equal amount. So there's no change in the time alignment of all the frequency components. They're all being uniformly shifted in time. They're not being realigned. They're not being distorted. And so that's a very desirable characteristic for our filters to have. Now this very busy chart is just showing you that on the left-hand column we have different shapes and different symmetries that the unit sample response for an FIR filter might have. And these are all cases that will produce a linear phase response in the discrete time Fourier transform frequency response. And the four cases are whether you have even symmetry around the center of h of n or odd symmetry around the center of h of n. And the other dimension is whether you have an odd number of samples in your finite impulse response or an even number of samples in your finite impulse response. Now there's four combinations there of odd and even lengths and odd and even symmetry. And it turns out that the kinds of filters that you can produce, high pass, low pass, band stop, depends on that combination. Depends on whether your unit sample response is an odd length or even length, and whether it's even symmetric or odd symmetric around its center. And this comes about because of the way the discrete time Fourier transform works, where certain symmetries that show up in the time domain infer and produce other kinds of symmetries in the frequency domain. And some of those symmetries that must be present in the frequency domain give rise to some shapes of magnitude response that make it either possible or impossible for me to make the particular filter shape I want. For example, if you have an odd length filter that has even symmetry, so I have an odd number of samples in the unit sample response for my FIR filter, and they're symmetric around the center, then it turns out that's the case that we usually use for linear filter design, because the symmetries inferred from that allow me to make pretty much any shape I want of frequency response, of magnitude response in the frequency domain. However, if I have what's shown here is the second row, a type 2 filter that has an even length, an even number of samples in its unit sample response, and has even symmetry around its center, that kind of filter, that kind of combination of symmetry, forces the frequency response, the magnitude response, to be odd symmetric around the Nyquist frequency. And so that means that I must have a 0 at the Nyquist frequency. And that's okay if I'm making a low pass filter or a band pass filter. But if I want to make a high pass filter, I can't use that, because for a high pass filter, I would need a magnitude response of 1 at my highest frequency, the Nyquist rate. This particular kind of filter can't do that, and so I can't use a type 2 even length, even symmetry, linear phase, FIR filter to make a high pass filter. Now, we won't go into great detail around this. If you're interested in this kind of filter design, we have other courses like EE328 and EE328 that get into these design rules, but just giving you a preview and letting you see that the length and the shape and the symmetry of the unit sample response has some direct consequences on the shape of the frequency response. And again, we really like this linear phase, this non-distorting characteristic of FIR filters. So a lot of the FIR filters that we'll design in this course and any future courses that you take will generally be these kind that have some kind of symmetry, usually even symmetry, in their unit sample responses. And again, typically we'll shoot for odd length filters that have even symmetry will be kind of our gold standard for a linear phase FIR filter. Now, numerically, if we have a linear phase filter that has a length m, meaning I have m b coefficients in my difference equation, then the phase delay and the group delay, because it's a linear function, turn out to be exactly the same thing. And those are usually expressed as the group delay, or little g, which are a constant, and they're related to that slope of that linear phase curve. If I have a finite length filter, we can have a simple expression for what that group delay is going to be. It's going to be the length of the filter minus 1 divided by 2. Now, a way to interpret that is that if I have a filter that has, let's say, 5 terms, 5 coefficients, b0 x sub n, b1 x sub n minus 1, b2 x sub n minus 2, and so on, down to b4 x sub n minus 4, the delay introduced by that filter is basically half the number of sample delays that I have in that difference equation, or about half, that on average I'm delaying them by half the length. Okay, so that's a finite impulse response example. Let's take a recursive filter, and one that has an infinite impulse response, and see if we can find the discrete Fourier transform frequency response of this filter. Now, this is the simplest recursive filter, and hopefully you would be able to construct the difference equation for this filter. Looks like y of n is x of n added to a feedback term that's alpha times the delayed output, or alpha times y of n minus 1. Now, if we wanted to find the frequency response of this particular filter, well, first we're going to need the unit sample response. This one I can't derive quite so easily as we did in the FIR case. I can't just substitute in x sub n equals delta sub n, because I have that feedback term, that y of n minus 1 term in there. And I'm not going to know quite what to do with that. So we can always break out a recursion table and substitute in a unit sample sequence, run that through the difference equation, and see what comes out, and see if we can infer the functional shape of the unit sample response. If we put in a delta sub n sequence, that's x sub n is 1 at n equals 0 and 0 elsewhere, and run that through the difference equation, we see that the output takes on the value of 1, then alpha squared, and alpha cubed, and you've actually done this one for homework. And from that, we see that the unit sample response is a form of alpha to the n u of n. Okay. Knowing that, first off, before we go and find the frequency response, we might ask ourselves, is this a stable system? And if you recall, for stability, we can look at the characteristic equation of this particular system. Now, for that, I want to rewrite this difference equation with all the y terms on one side and x terms on the other. So let's do that. Now I can easily pick off the characteristic equation for this system. It looks like 1 minus alpha times z to the minus 1, and the homogeneous solution is equal to 0. Multiplying everything through by z, you get z minus alpha is 0, z must be alpha. Now, to be a stable system, we want z, the root to the characteristic equation, to have a magnitude less than 1. And so if we limit ourselves to that case, we'll have a stable system. So let's do that. Now, if I want to find the frequency response of this system using the defining summation, not an FIR filter anymore. For IIR filters, or for infinite length signals, So if x of n is infinitely long or h of n is infinitely long, I'm not going to want to write out the individual terms of the summation, but what we're going to want to do is describe x or h using analytical functions and then see if there is a closed form solution for the geometric series summation that results with that complex exponential using some lookup tables, not for the transform, but for the summation itself. And so here's an example of the kind of summations you might find in a math textbook. Um, some of these we've already used in the prior slides, but here's a more complete set that if we have any of these summation forms, we can simply look up the summation results. So with our recursive filter, we found the unit sample response is an alpha to the n u of n. That depends on alpha, of course. Now, if we're going to to find the frequency response, we'll take the discrete time Fourier transform of that, and that's actually the same example we've done a couple slides ago, where we had an alpha to the n u of n exponential sequence. We factor out the exponent n so that we can have a sum from n equals 0 to infinity of a to the n, which we know is 1 over 1 minus a as long as a is less than 1. And we did say for stability we were going to have to insist on that anyway. So we substitute that in, and we have our same result we had before, that the frequency response is 1 over 1 minus alpha e to the minus j2 pi f. And we've already derived the magnitude and phase for this one. And we have the magnitude function and the phase function. Again, you should correct this and have a minus sign in front of that inverse tangent. Now, that brings us to our second method, which is going to be ultimately our most preferred method for doing discrete time Fourier transforms. And that is, once we've derived the transformation relationship, let's not do it again. So if we're working with common signals or common functions, instead of running them through the defining transform summation and doing it mathematically, we'll actually just use a lookup table to find the transform values or the inverse transform values, just as you did in 228 with Fourier transforms and Laplace transforms. So what we're going to need then is a table of values that we can work with, a table of transforms where we can look up time domain functions and find their discrete time Fourier transforms, or if we're doing an inverse transform, look up the f functions, the f forms, and see what their inverses are. Now notice there are two different versions of the discrete time Fourier transform that usually show up in these tables. The kind we've been using, where our explicit variable is capital F, digital frequency in cycles per sample. There's also an omega form, which some texts use a capital omega, some use a lowercase omega. Just as there was two versions of the continuous time Fourier transform on whether you're using a Hertz kind of frequency or a radians per second kind of frequency. Here in the discrete time version, we would have a frequency variable that's capital F as cycles per sample, and the omega form would be radians per sample, would be the units on that. Oftentimes we run into the case where we have a function we want to transform that looks similar to one of these signals that we have in the table, but not exactly the same. Sometimes they're subjected to time shifts or index reversals or some compression or expansion argument. And so we need to be able to modify these transforms using some knowledge of the different properties of the Fourier transform. That is also usually captured in tables such as this that show us if our signals are subject to certain modifications, how does that then modify the discrete time Fourier transform. And next time what we'll do is go and look at these in more detail and see if we can understand where some of these properties come from and how to operate with them and how we can use them to help us find discrete time Fourier transforms. But that's about enough for now. I hope you've understood this, and we'll take questions on it next week when we're back together. and add on to our knowledge of discrete time Fourier transforms as we look at how we can do these computations, how we can use them, and then ultimately what we actually came here for is to try to simplify our process of system analysis by using these transforms and using some of these properties that are on this chart here, particularly the convolution property, to let us do discrete time system analysis using these transforms. We'll see you on Monday.